Okay, good morning, everybody. So it's my great pleasure to be here today. So Turkey is a great country, and I'm very happy to be here. So Baris, thank you very much for the nice introduction. So my name is Masashi Sugiyama. So I'm coming from Japan and from University of Tokyo and RIKEN. So let me briefly talk about myself with one slide. So currently, I'm director of an AI center called RIKEN Advanced Intelligence Project Center. So this was started 3-4 years ago from 2016. And now actually the center is really growing, and we have about 700 members in the center. So covering from fundamental theory to applications and also ethics of AI. Then at the same time, I'm professor at the University of Tokyo, and also the lab is really growing, and now I have about 50 students in the lab. But still, we need even more people in this AI field. So I decided to work as part-time consultants at several local startups in Tokyo. So we try to also involve some engineers from industry. So personally, I have worked on theory and algorithms of machine learning, so quite fundamental stuff. But recently, so these fundamental issues are really useful in real world. So I can really directly talk with industry partners to apply for our new algorithms and have some feedback. And also, I'm interested in exploring real-world applications, including robotics. But clearly, it is impossible for me. So I'm just a theoretical researcher, and I can't really do any applications by myself. So that's why I decided to have partners outside. Some are from industry, and some are from other national research centers. And I have explored a lot of different fields, like signal processing, image analysis, natural language processing, brains, cars, robots, optics, advertisement, medicine, biology. But they are done by my partners. I'm just doing machine learning by myself. And my personal research goal is to develop practically useful algorithms that have theoretical support. Of course, it's not that difficult to use a lot of heuristics to improve the performance. We have many students, they try a lot of different ideas, and we can choose the best idea. But in the long run, this kind of heuristic approach doesn't really work. It's not sustainable. So I believe it's quite important to have a nice theoretical foundation for machine learning and build upon this foundation. Of course, at the end, we need some heuristics to improve the performance. But as far as possible, we try to develop fundamental stuff as high as possible. Then at some point, we switch to heuristics and really apply to our technology to real-world problems. So that's my standpoint. So far, I have published several books on fundamental machine learning stuff. OK, so then what is my talk about today? So machine learning from big data is really successful everywhere in speech recognition, image understanding, robot control, natural language translation, and things like that. But these applications are successful because we can easily get labeled big data. Well, I shouldn't say easy. Many companies are spending a huge amount of money to label data. But in other applications, we can't really get massive label data. For example, at our RIKEN Center, we are working on some medical research like cancer or dementia or natural disasters, because we have a lot of earthquakes and typhoons in Japan. Or we are also interested in robot control or brain signal analysis. So in these applications, human is always involved in the data collection process. So it's not really possible to collect millions of data points. So we have to always work with a small number of data points. So that's the challenge here. And there are many approaches to coping with this kind of label cost problem. For example, we just improve the data collection process, like using crowdsourcing. Or we may use a simulator to generate pseudo data. So this kind of approach is quite popular in natural disasters or some chemistry and physics experiments. Or we may just use domain knowledge. So we have a lot of engineers really working in those fields. They have nice heuristics, and we just encode those heuristics. Or we use cheap but weak data. So for example, unlabeled data can be easily collected. Like semi-supervised learning is a typical idea for the last part. This one. So my focus is the last one, use cheap but weak data today. So I introduced our recent advances in classification from weak supervision. So I will go into more technical detail later, but we don't say we only have a small number of data points, because it is impossible, theoretically impossible to learn something from a small number of data points without having strong prior knowledge. So my basic idea is that something is many, and we try to use those many weak data points to improve the performance. So that's the basic idea. And then the target problem today is extremely simple. I think everybody knows, binary classification problem. So we are given blue points and red points, and we just want to separate them. That's it. Suppose the number of label data is n. Then we know that the estimation error of the boundary decreases in the order of 1 over square root of n. So it's a function like this. So this is why we want to use big data. Like if we have like 100 times more data points, then the error decreases in 10%. So this is generally guaranteed. So it's a kind of law of large numbers or central limit theorem and things like that. But as I said, so collecting label data is often quite costly or sometimes impossible. Then let's consider the extreme opposite. It's unsupervised classification. So gathering label data is costly, so let's use unlabeled data, like black ones, that we don't know whether they are red or blue, but they are still black. Then this unsupervised classification is typically clustering. So like in this case, we have 2 clusters. It's a famous 2-moon data set, by the way. So we have 2 clusters. Then we may split these two clusters in this way. Then if one cluster by chance corresponds to one class, then this method works perfectly fine. Like if this cluster are all red and this cluster is all blue, then clustering works perfectly fine as a supervised classification method. But in reality, life is not that simple. So this kind of naive approach doesn't work. Then, so many people have worked on semi-supervised classification for long years. So they try to use a large number of unlabeled data in addition to a small number of labeled data. Like I'm still using the same illustration, but now we have one blue point, one label point here, positive point here, and one negative point here. But typical semi-supervised classification methods are basically the same as unsupervised classification. They do some kind of clustering, either explicitly or implicitly, like having this kind of line anyway. But now they have like blue point here and red point here. So let's propagate this blue color over this cluster, or this red color over this cluster. So this is the basic idea of standard semi-supervised classification. But then it is clear that this method suffers the same problem, same weakness as the previous unsupervised classification, unsupervised clustering method. So if one cluster corresponds to one class, this works well. But in reality, it's not really true. Like we had a large number of papers on this kind of semi-supervised classification, but they are typically working well only for MNIST data set, so number data set. So it's perfectly fine. So if we have one label data point, then it works almost perfectly. But for other real-world problems, unfortunately, this simple approach does not work well. So then so far, the summary is like this. So we had supervised classification, unsupervised classification, and semi-supervised classification. And I took the classification accuracy on the horizontal axis, low, high, and also labeling cost, low, high, on the vertical axis. Then supervised classification works quite well, but it requires the highest labeling cost. On the other hand, unsupervised classification, it does not require the labeling cost, it's the lowest cost, but classification accuracy is low. Then semi-supervised classification. So we expect this to work much better, but unfortunately, it doesn't work so well in many practical problems. So then it is still located in the left-hand side of the figure. So then this space is our target. So we are interested in developing classification methods that achieve high accuracy with low labeling cost. So that's the target of my talk today. So is everything all right so far? OK, good. So then next, so this is the kind of table of contents of my talk today. But so this is in the morning. So I will spend next 10 minutes to go through the entire contents without going into the technical details. So I'm just explaining what kind of problems we can solve by the latest technology. Then later, I explain how we solve the problem. Maybe for some people, how part is not that interesting. Then you may just focus on the next 10 minutes and see what kind of problems we can really solve in practice. So they are called like PU classification, PNU classification, blah, blah, blah. So I use a lot of acronyms like PNU stuff here. P is positive, N is negative, U is unlabeled. Then conf is confidence, S is similar, comp is complementary. So I use these shorthand notations later. Then let's start from PU classification. So as the name stands for, we try to train a classifier only from positive and unlabeled data. So remember that still the problem is the binary classification problem. We want to separate positives and negatives. But because of some reasons, we can't get any single negative points, but only unlabeled data and positive data. For example, if we consider click prediction problems on the web, so we can easily collect positive data by looking at the clicked links, so click history. But collecting negative data is not that straightforward, because negative here means so users don't like this link or that link. Of course, we can easily collect links that were not clicked by the user, but we can't simply say unclicked links are like uninteresting links for the user. Maybe user had interest in this link, but he or she didn't have time to click this link at that moment. Then that sample is still, that link is still unclicked. So in this scenario, we naturally only have positive data and unlabeled data without any negative data. And similar kind of situation can happen also in like friend prediction in SNS networks, for example. We can actually find a lot of real-world problems where negative data is not available. So the situation is like this. So we have blue points and no red points, but only black points like this. And only from blue and black, we want to obtain this green line. So that's the PU classification problem. And I will go into the technical detail later, but our conclusion is that this problem can be basically completely solved. So in our life, we don't need negative data at all. Just give me positive and unlabeled data, then we can perfectly train a classifier. So that's our theoretical results so far. And we can achieve 1 over square root of n convergence. So this is actually theoretically known to be the best convergence rate without any additional knowledge. So that means already like PU classification is optimal in terms of like data efficiency. So that's PU learning. Now we can solve a classification problem only from P and U data. Then based on that method, we can actually perform semi-supervised classification in a bit better way. So I call semi-supervised learning as PNU classification, because it contains all positive, negative, and unlabeled data. So blue, red, black points like this. Then our idea is extremely simple. So we decompose this PNU problem into PU, PN, and NU problems. Then already I have shown, I just explained that we can solve the PU problem in a nice way. I will talk about it later. Then NU problem is basically the kind of symmetric version of PU problem. So we can also solve this problem in the same way. Then the last one, PN problem, this is the standard supervised learning problem. Of course, we can solve it. Then just by kind of combining 3 problems, we can solve a semi-supervised learning classification problem. So that's the idea. So we didn't develop anything new, but we just decompose the problem into PU, PN, and NU. Then actually we can achieve the optimal convergence rate again. So I will go into the detail later, but so we don't really need any additional theoretical assumptions on unlabeled data, like clusters. So all previous methods basically required some kind of cluster assumptions, like one cluster corresponds to one class. But our method doesn't require that. But still, we can guarantee that it achieves 1 over square root of n convergence. So that's PNU classification. Then the next one is P classification. So sometimes even U data is not available. For example, if you work for a company and you can access the database of your own company, but of course you are not allowed to see the database of other companies, so because of some privacy issues. So this means that you are not allowed to even get unlabeled data from other companies' databases. So then we can only see the positive data, one of the classes from the database, from our own database. Then, so basically the conclusion is that if we only have P data, it's not possible. So it's basically one class classification problem, and we can't really solve the classification problem in a systematic way. But we have shown that if the positive data is equipped with confidence, so I will define the confidence more specifically later, but it's class conditional probability. If we have positive data with class posterior probability, then we can really train the classifier. Again, with the convergence rate of 1 over square root of n. So this means that we don't even need unlabeled data, negative data, but we just need positive confidence data to train the classifier. So that's P-conf classification. Then let's further reduce the supervision. So now it's completely unsupervised. But of course, unsupervised classification is different from supervised classification. So we have a bit additional situation here, assumption here. So it's called UU classification. So we have two sets of unlabeled data. But our assumption is that so two unlabeled data sets have different class pairs, meaning that different proportions of positives and negatives. Like this is one of the unlabeled data sets, and it has, I forget, 50% positives and 50% negatives or something like that. Then this is the second unlabeled data set. This has 70% positives and 30% negatives or something like that. They have different proportions of classes. But here, actually, we don't have to know the proportions, but we just have to assume theoretically that proportions are different. Because if the proportion is the same, so given a single unlabeled data, we just split it into two data sets. But this is just redundant. So we need to assume that pairs are different. But once we have two unlabeled data sets with different class pairs, then we can again solve the classification problem. So even without having any single label, we can draw a decision line like this. But one small remark here is that because we don't have any single label in this situation, we can't really know which side is positive or which side is negative. So we can just draw a line between two classes. So maybe we need one label data to see which side is positive or negative. But without having any label data, we can draw a line between two classes. And again, with the convergence rate, 1 over square root of n. Then next one is a kind of variation of UU classification. So it's called SU classification. So let's consider delicate classification problem, like about your salary or your religion or your political opinion and things like that. Sometimes you don't really want to say yes or no explicitly because it's a kind of private problem. But sometimes it's easier to say, okay, my opinion is same as that person, or these two people have the same opinion, or something like that. So that's a similarity pair, like this. This person has the same opinion as this person. This person has the same opinion as this person. But we don't know whether they are positives or negatives. And we have shown that only from like similarity pairs like this, and also unlabeled data, we can really train a PN classifier again. We can draw a decision line. Again, we don't have any single labels in this case, so we can just draw a line, and we don't know which side is positive or which side is negative. But still, we can draw a line. So this is a kind of special case of UU classification. So we can also solve this problem, again, with the convergence rate 1 over square root of n. Then finally, so this is the last method. So it's called complementary classification. So only in this slide, let's consider multi-class classification problem. Now we have classes more than 2, like 3 classes like this. Or in some image classification problem, for example, we can easily have like thousands of classes nowadays. So in that kind of super multi-class problems, so labeling data is actually quite costly, because we often use crowdsourcing to label images, for example. Then, so we have, let's say, 1,000 classes. Then each crowd worker has to go through the entire list of like 1,000 labels and try to find the right one, like a sky or cat or dog or something like that. Then somewhere here, you can find the right label. So this takes like a lot of time to label a single data point. So it's quite costly. So then our idea is, okay, let's give up having the correct label, but instead give me wrong labels that are guaranteed to be wrong. Like, this is not a cat, this is not a dog, this is not a sky, this is not class 1, like that. Actually, obtaining such a not label that we call complementary label is quite easy. Because if we have a 1,000 classification problem, then so only one is correct and other 999 are all wrong. Then if you just randomly pick one of the classes, this is almost always wrong. Then just you have to guarantee that this is wrong. Then actually we can train a classifier. So again, the conclusion is that only from complementary labels we can train a classifier. And again, the convergence rate is 1 over square root of n. So we have a bit trick behind here, this number, but only from wrong labels we can train a classifier. So collecting wrong label is much cheaper than collecting correct labels. So that's the idea here. So this is complementary classification. Okay, that was the entire story today. And if you are already happy, then you can go for coffee. And if you want to know the secret behind, then from now, so please listen to my talk for another 1 hour or so. Is everything all right? Good. Then, so I will go into the detail one by one. And after each section, hopefully I can have some questions. Because once I go to the new section, then it's basically a new story. Then before going into the technical detail, I need to say a bit about some notations. So based on standard supervised classification. I call it PN classification because we only have positive and negative data. So I think most of you are familiar with basics machine learning, like binary classification. So let's just quickly go through some notations. So I consider label data pair of x and y. X may be d-dimensional real vector, and y is typically +1 binary label. And we have endpoints and independently and identically drawn from P of x and y. So that's a standard setup of machine learning. Then, so we consider classifier F. So that's a mapping from input x to output y. Then this, the sign of the output of the classifier is regarded as a predicted label, y hat. And as function F, classifier F, we can basically use any classifier. Typically, I consider a linear model for simplicity. But we can also use additive model or kernel model or deep networks or LSTM, CNN, whatever. Any F is fine. Then I also use the notion of margin. So that's the product of label and its label prediction, Fx. So if margin is positive, then basically sign of our classifier is the same as the correct label. So classification is correct if margin is positive. And if margin is negative, then classification is wrong. So we want to maximize the margin to train a classifier. And to evaluate the performance of the classifier, we typically use the 0-1 loss. So it's the count of wrong classification. So by equation, it's defined like this. But this is basically just counting the number of wrongly classified data points. So 1 for correct prediction and 0 for wrong prediction. Then, so based on the 0-1 loss, we can define the classification error. So 0-1 loss is expected over all data points coming from P of x and y. So that's the classification risk, classification error. So expected 0-1 loss over all data points. So our real goal is to find a minimizer of this R01, so classification error. But unfortunately, this problem cannot be solved in real time because P of xy is unknown. So let's use samples instead. So this expectation cannot be computed directly. So instead, we use IID samples. Then this expectation is basically approximated by the average of samples, IID samples. So it's the same as we know 6-faced dice from taking 1 to 6 with probability 1 over 6. Then we know the expectation is 3.5. But suppose we don't know this number, 3.5. But we can estimate it by throwing the dice many times and taking the sample average. So we are just doing the same thing. So we don't know the true expectation here, but we have samples. We just compute the sample average. Then actually we can show that this is actually the optimal approximation to the true expectation without any additional assumptions. We know, so this R hat is equal to true R with order of 1 over square root of n. So this square root of n actually coming here. So this is the kind of theoretical limitation we can't get rid of. So basically, we just replace expectation by sample average. Then, so the problem is almost solved. But still, minimization of this R hat 01 is not possible in practice because it's NP hard. So we don't have an algorithm to solve it in a polynomial time. Because of this kind of discrete nature of the 01 loss. So now the horizontal axis is the margin M. So then 01 loss is this kind of step function. So to avoid this problem, let's use a smoother loss function. Then we have like a lot of variations. Like for this black curve, it's an exponential function. So this actually corresponds to boosting, like other boost or whatever. Or if we use this green line like this, so it's called hinge loss. So this corresponds to support vector machine. Or this purple curve is a logistic curve. It's called logistic regression used in statistics. Or this light blue curve is the ramp loss, and it's used in robust support vector machine. So almost all like well-known machine learning algorithms can be basically accommodated in this framework by just changing the loss function and maybe adding some regularizer. So they are called surrogate loss functions. So then based on this surrogate loss L, so we define the classification risk like this. So this is basically our target. We try to minimize this quantity in practice. Then again, so we replace this expectation by sample averages. Then we have this R hat Pn. And again, this is the best approximator to this true risk with the order of error of the order of 1 over square root of n. And we try to minimize this R hat Pn in some function class, either linear model, additive model, kernel model, or some deep networks. So that's the basic framework. But here, actually, we use positive and negative data, so Pn learning. But from now, so let's forget this part, because now we are weakly supervised learning situation. We don't have both positive and negative data, but we have some other things. But still, we want to try to minimize this true risk, classification risk. So that's the target here. OK, that was a kind of quick review of like standard machine learning setup. And is everything all right so far? Maybe that was a bit boring part. But if you want to see some equations later, you can see the slide from here. OK, then let's come to PU classification. So again, the problem is, so we have only positive data and unlabeled data. So positive data are IID samples from the positive class distribution. And unlabeled data is an IID sample from marginal distribution. And based on blue and black points, we want to train a PN classifier. So then again, we have the same definition of the classification risk. And in the standard PN case, we basically decompose this one into risk for positive data and risk for negative data. Then in the standard PN case, we have both positive data and negative data. Then we can just replace this expectation by sample average and also replace this expectation by sample average. Then we can solve the problem. But in this PU learning setup, we don't have negative data. So we can't directly replace this expectation with sample average. So that's the technical challenge here. And also, we have pi here and 1 minus pi here. So this is class barrier probability. So in unlabeled data, we have, let's say, 10% of positive data points and 90% of negative points or something like that. So it's pi. And in reality, we need to also estimate this pi only from positive and unlabeled data. But already we have several reasonable methods to estimate pi only from PU data. So today, I assume that pi is known already, or pi has been estimated in advance, and just use a fixed value. But in reality, we also have to estimate pi from data. But for simplicity, so let me avoid discussing this problem today. So then, so this part. So we don't have negative data, but we want to approximate the expectation over negative data points. So this is the challenge here. But we have a very nice, simple trick. We know that unlabeled data is a mixture of positive points and negative points, positive density and negative density. Like we have positive data density like this and negative data density like this. Then proportion is pi and 1 minus pi. Then unlabeled data distribution is something like mixtures of two densities. So this is, by definition, this is correct. Then this is already fine, because we have unlabeled data that corresponds to px, and we have positive data that corresponds to this blue density. Then information about this red density can be estimated by moving this term to the left-hand side. So that's the only trick. So in reality, I just move this term to the left-hand side. Then we have this kind of relation. And plug this one into this part, or including this part. Then we can basically decompose the second term into two terms like this. So that's the only technical trick we have done here. So then expectation over negative data does not appear anymore. We only have expectation over positive data here and here, and expectation over unlabeled data. Then all expectations can be approximated by sample average of positive and unlabeled data. Is this clear? And that's the most difficult part of this PU learning. So this is done. So then we can estimate the risk in an unbiased way, and it is straightforward that we can achieve 1 over square root of n convergence. Yeah, like we have sample average like this. Then we can achieve 1 over square root of n convergence. So more specifically, so we computed the difference of the risks of like empirical risk minimizer and true risk minimizer like this. This is upper bounded by this quantity. But we have 1 over square root of np, number of positive data points, and 1 over square root of nu, so number of unlabeled data points. We have this kind of theoretical guarantee. And this already shows that it's optimal. None of the methods can improve this approach anymore. So this is fine. So it's a very kind of straightforward approach, but we can solve the PU problem by this way. So that's the kind of end of the first part of PU learning. It's a like happy story so far. But unfortunately, it doesn't work so well. So we need to talk a bit more about some correction. But before going into that, so let's have a similar theoretical analysis for PN classification, standard supervised classification. Like the first line is the same as the previous page. Then we can also perform the same kind of analysis for standard PN classification. Then we have quite similar result like this, 1 over square root of np and 1 over square root of nn. So this is again optimal. But the interesting thing is now we can actually compare these two bounds because we have the same constant here. Then surprisingly, PU bound can be smaller than PN learning if this condition is satisfied. So this condition is just coming from comparing these two bounds. So this means that, initially I started PU learning talk because it's a kind of compromise. We can't get negative data, but instead we have unlabeled data. So let's use unlabeled data. So that was the starting point. But under some condition, we can actually show that PU learning can be better than PN learning. In particular, if you have a large number of unlabeled data, then this term becomes really small. Then maybe left-hand side tends to be small. Or if you have only a small number of negative data, then the right-hand side is quite large. Then PU learning can be better. So this means we have a certain number of positive data points, and suppose we have only small number of negative data and a large number of unlabeled data. Then instead of doing PN learning based on positive data and small number of negative data, using PU learning with positive data and a large number of unlabeled data is actually really better in terms of the upper bound of the estimation error. So I will show some experiments later, but this is really the case in reality. So if you have a large number of unlabeled data, then actually don't believe small number of negative data. So relying on large number of unlabeled data is actually better. So that's the finding here. So then one more challenge here. So actually that method does not unfortunately work so well in practice because of this reason. So what we have done so far was we decomposed the risk into P and N. And then N risk was kind of decomposed further into like this term and this term based on this relation, mixture relation. Then actually the problem is this minus. So suppose the loss function is non-negative. Then by definition, this risk for N data is non-negative because it's just an expectation over non-negative quantity. Then by definition, this expression is still non-negative because it's just an equivalent expression. But in practice, we approximate this expectation by sample average like this, and also approximate this expectation by sample average like this. Then this estimated quantity can be negative. Like originally, maybe this was 5 and this was 3, and 5 minus 3, so it was positive. But now 5 is estimated by data, and it has some estimation error. Maybe 5 becomes 4. Then this 3 is also estimated by data. Then maybe 3 becomes 5 or something like that. Then this becomes 4 minus 5, and it can be negative. So this really happens in particular when we use a flexible model like neural networks. So that's actually a problem. So its PU empirical approximation can be negative due to the difference of approximations. So this kind of problem didn't happen in standard PN learning. But now in PU learning, we have negative sign here. And that actually causes a problem. But we have a very simple solution to this problem. So we had like these two terms that can become negative. Then, okay, let's impose this to be non-negative. Just we take max 0. Once this term becomes 0, let's round it up to 0. That's it. So this one-line extension gave us a new RIPS paper 2 years ago. But actually, this is really problematic. Because if you see the experiment here, so suppose we perform standard PN classification. Then the training error, this dotted line, decreases nicely like this. Then test error, this blue solid line, this also decreases and converges nicely like this. So this is a standard PN classification. But in the PU learning case, the training error, this red dotted line, decreases like this. And then at some point, it becomes negative like this. Then the test error actually grows like this. So this is a clear indication of overfitting. So this term should be non-negative by definition. But because of this minus sign, it can become negative. Then we have clear overfitting. So that's why we decided to have this kind of constraint, max 0 constraint, to keep this term non-negative. But now the risk estimator is biased because of this max 0 operation. So we need a little bit more like justification for this. So then I don't really go into the detail, but we have some theoretical analysis for that. And taking max 0 is better in terms of so okay, by max 0, it is biased, but it is still consistent, and its bias decreases exponentially fast. So basically, we can ignore the bias. But because of this small bias, mean squared error is improved. It's smaller. And then also the risk of a linear estimator is also optimal. So we can somehow justify the use of this biased estimator as a better one. And indeed, it works actually quite well in experiments. So we did something a little bit more realistic experiment for CIFAR-10 data set, so binarized version. So then again, for standard supervised learning, the training error decreases like this, and it converges to 0 like this. Then test error decreases like this and converges like this. So this works reasonably well. Then for PU learning without correction, so again, the training error goes negative like this. Then test error, again, grows like this. So it doesn't work. But once we have max 0 correction, non-negative PU learning, then the training error is kept non-negative like this. Then test error is also kept lower like this. Then as you can see, so here, test error, in terms of test error, PU learning is smaller than PN learning. So actually, in this setting, we have a large number of unlabeled data and only a small number of negative data. Then doing PU learning is actually better than PN learning. So we can improve supervised learning by using a large number of unlabeled data. So that's a kind of nice result here. OK, so this is the summary of PU learning. So I talked a lot about PU learning. So things are a bit complicated. But in the end, so we are just given blue points and black points. And what we have done is to just separate blue and black. So we basically regard black points as negative. This is partially fine, right? So because black points contain blue and red points, and some red points are contained. So we can regard it as negative. But of course, if we just directly separate blue and black, it is biased. because black points contain also positive data. Then, so what we have done basically was to correct that kind of bias. Like more specifically, so suppose we use a loss function L, then we use loss function L for unlabeled data, and loss function L tilde defined in this way for positive data. Then we can actually completely remove the bias. So in a sense, this is a kind of noisy classification problem. So we have positive data. This is noiseless, all positives. And we have unlabeled data. We regard it as noisy negative points. So some are red and some are blue. So they are noisy negative points. And it's a kind of asymmetric problem, right? So positive data is noiseless, but unlabeled negative data is negative. Negative data is noisy. Then this asymmetry can be kind of somehow coped with by using this L tilde function. Then we can show the optimal convergence rate. And we have some nice properties, like if L satisfies this condition, like ramp loss, then so we are basically using the same loss for P and U. Or if L tilde is a linear function that is satisfied by logistic loss or double hinge loss or squared loss, then the optimization problem becomes convex. So it's quite convenient. And for deep nets, as I explained, rounding up the empirical false negative error to 0 can really significantly improve the performance. So that's the end of the PU classification part. And do you have any questions so far? So a lot of equations are there. But in the end, so we are just separating blue and black. And regard blue as noiseless positive. And regard black as noisy negative. And just perform classification. Then we can train a classifier without having any bias. So that was the basic idea. Clear? So we have a toolbox already on the web on GitHub. So if you download it, you can solve a classification problem only from P and U data. OK, good. So then the next is P and U classification. The heaviest part was done. So the latter is actually simpler. So P and U is, as I explained, it's a semi-supervised classification method. We have positive data, negative data, and unlabeled data. And we decided to decompose this problem into PU, PN, and NU. And we have already PU classification method and NU classification method. And also, we have standard PN classification method. So just combine their learning criteria. But in what way? So a natural choice would be to combine PU and NU, because they look symmetric. So we started from this combination. Like we have gamma parameter, so 1 minus gamma R PU, risk of PU, and R times risk of NU. So this is simple, and this looks fine. But it turned out that in experiments, this combination does not work. Then we did some theoretical analysis for this decomposition. Then we found that, OK, I don't really have time to go into that theoretical detail here. But once PU is better than NU, then NU is actually not good, or NU is not good. Or if NU is better than PU, then PU is really bad. So in a sense, combining PU and NU are not really the best combination. So according to this theoretical analysis, we can show that PU and PN, or NU and PN, are the best combinations. So it's a bit asymmetric, but we found that this is better theoretically. So then in the end, the proposed method is just simple. So we have PU learning here, PN learning here, and NU learning here. And we have one hyperparameter, eta, that takes a value from -1 to +1. And if it's -1, it's completely PU, no negative. Then once eta is increased, we have more influence of PN. And if eta is 0, it's just PN, no unlabeled data. Then eta is further increased, we have more influence of unlabeled data. And then in the end, if eta is 1, it becomes NU. So this just having one hyperparameter is actually sufficient from the theoretical viewpoint. And the equation is a bit complicated, but it's just like this. Then actually, this is a very simple method, but theoretically quite attractive. Because we can show that the generalization error of a classifier is upper bounded in this way. Then we have 1 over square root of np, 1 over square root of nn, and 1 over square root of nu. So these are the number of data points. So this is actually a very good result, because we had a long history of semi-supervised classification in the last 20 years or so. But none of the methods achieved this 1 over square root of nu convergence without having additional condition on unlabeled data. Like previous method almost all require the kind of cluster assumptions, like one cluster corresponds to one class or something like that, manifold smoothing or something like that. But without having that kind of assumption, our method can achieve 1 over square root of nu convergence. So this is the optimal rate. So meaning that we can really utilize unlabeled data in a variable way. And more technically, so we use unlabeled data in a different way than the previous methods. Like we use unlabeled data for loss evaluation. Because as I said in the PU learning section, so we regard unlabeled data as noisy negative data. So we are kind of really labeling unlabeled data implicitly. So that's why we are using unlabeled data for loss evaluation, and we can achieve this convergence rate. But on the other hand, in the previous methods, so just unlabeled data is used for regularization or manifold smoothing, just propagating label over cluster. So it cannot be used for reducing the bias, but just adding the bias and reducing the variance. So in a sense, the use of unlabeled data is completely different in the previous methods and our method. And that's why we can achieve this 1 over square root of nu convergence. So technically, it's nothing new. It's just a combination of PU learning. But this is a kind of theoretically ideal semi-supervised classification method. And if we do experiments, then, okay, in practice, I can't say the new method works really well every time. Because at least we can say it's safe. Because in previous semi-supervised classification method, sometimes the performance is really bad. Because they need cluster assumptions, and once the cluster assumption is violated, then the performance is really bad. But in our case, the performance can be somehow guaranteed because we have a theoretical upper bound like this. As long as we have many unlabeled data, it doesn't hurt the performance. So performance is kept reasonable. So that's why if we do a lot of experiments, then our method is not necessarily always the best, but it's always one of the best. So it's quite stable, reliable. So that's actually quite important in practice when we use semi-supervised classification. Okay, that was PNU classification. And do you have any questions? Yes.
Is there a limit to how much unlabeled data you can use?
Limit for?
For how much unlabeled data you can use? Is there a limit after which more unlabeled data harms the classifier?
So in our case, if you have more unlabeled data, the performance is not getting worse. It is the same. Just we have more computation time, and maybe at some point we have to stop, but it's safe. All right. Okay, so then PNU part was done. Then the next challenge is PConf classification. So we only have positive data. So this part is quite simple. So now the data is pairs of X and R. X is an unlabeled data point. It's a positive data point, actually. Positive data point, and R is its confidence, class posterior probability, positive probability. Like this point is 95% positive, this point is 70% positive, this is 5% positive, or something like that. And only from this XR paired data, we want to train a classifier. So that's the target here. But already we have a recipe. So the same way, we first define the classification risk, and we try to estimate this risk only from PConf data. But in the PConf case, naively, suppose one point is 80% positive, then we can say it is 20% negative, right? So then we may want to write a risk in this way. So R positive and 1 minus R negative, and add them together and take the expectation. So this is a kind of naive solution. But we can show that this is unfortunately not correct. So it's not equal to the risk. The right way is, after a few lines of calculation, we can show that it is like this. So it's quite similar, just divided by R and having pi here. But this is the right expression. So technically, so this is actually not really bad, but the distribution is positive. If this is expected over P of unlabeled data, then this is correct. But we only have data points from positive class. So that's why actually we need a kind of importance sampling to correct the distribution difference. So that's the solution here. And one nice thing about this expression is that pi is here, so class prior probability. And in the PU case, we had to estimate pi from data. But in pconf case, this is just a proportional constant. So we can basically throw it away. And we just have to minimize this only from data. So it's much simpler. So that's pconf classification. And this simple method is just empirical risk minimization. So again, we can show that the difference of the estimation error is upper bounded by 1 over square root of n. So it's the optimal convergence rate. So it's nothing technically new, but it is a kind of safe guarantee. So optimal parametric convergence rate can be achieved. So then doing experiments is actually not that simple, because once we compare pconf method with pn method, of course pn method works much better. So theoretically, pconf has the same convergence rate as pn learning, but of course pn is much better in practice. But once we compare pconf method with the wrong method, so just weighted method here, this one, we know this is wrong, so it doesn't work. So this is much better. So we can't really have like a nice comparison here, but anyway, we can train a classifier only from pconf data. And for some data sets, pconf result is rather close to supervised learning, PN learning. So this works reasonably well. So we can train a classifier only from pconf data. So that's the pconf part. And any questions? Oh, yeah.
What do you think about novelty detection or anomaly detection when we have access only to positive data?
Ah, yeah, thank you very much. That's a very good point. So actually, PU learning can be, okay, this is also a kind of anomaly detection. Like we have, let's say, maybe normal data as positive, for example. Then we regard this is very normal and this is slightly abnormal and something like that. If we can rank samples in that way, then we can immediately use this approach to classify either anomaly or normal or something like that. And also, PU learning can be used in the same way. Like positive data can be regarded as like normal points, set of normal points. Then unlabeled data can be regarded as like mixture of normal points and anomaly points. Then we can use like PU learning to obtain a classifier between anomaly and normal samples. But we don't need any single like anomaly examples because it's often difficult to obtain. We can completely avoid that problem, but still we can solve the problem. Okay, thank you very much. That's a very good point. All right. Then, so let's change the story a little bit. Now, UU classification. It's unsupervised classification. So we have two sets of unlabeled data. Both are coming from P and P prime, like this. And our assumption is that class pairs are different. Py and P prime y are different. 50-50 and 70-30 or something like that. But class conditional distributions are the same. Like both are actually Gaussians in this case. Then, so our previous paper showed that the sign of the difference of the class posterior is a kind of definition of the optimal classifier. This is a base optimal classifier. And we can show that this can be expressed in this way under uniform test classifier. So we have one more data set in the test phase. And we assume that in the test phase, we have 50-50 positives and negatives. Then the optimal classifier can be expressed in this way. So C is a constant taking plus 1 or minus 1 based on class pairs. But there's no way to estimate this because we only have unlabeled data. But actually, sign of C is not that different, not that important, because just estimating sign of P minus P prime gives us this boundary. So by that, we can solve UU classification problem. So given two sets of unlabeled data, estimating P and P prime from two sets and take the difference and take the sign, then we can solve the problem. So that was the basic framework we developed a long time ago. But now we have slightly more like systematic approach based on empirical risk minimization. So again, so following the same recipe, So we define the classification risk like this. Then now, we need some additional assumption. The loss function satisfies some kind of symmetric condition. Then the risk can be expressed in this way. So we have some hidden constants here and here, and it's the expectation over unlabeled data of first set. This is expectation over unlabeled data of the second set, and some constant. Then, so based on two sets of unlabeled data, we can just use empirical risk minimization like this. Then we can train a classifier. So again, it's a standard recipe, so we can achieve 1 over square root of convergence like this. Now we have two sets of unlabeled data, but we have the same optimal convergence rate. So it's a bit special problem, but so actually the intuitive meaning of this approach is that in the PU classification case, we regarded P as noiseless positive and U as noisy negative. But in the UU classification case, actually both are noisy. First U is regarded as noisy positive data, and the second U is regarded as noisy negative data. Actually, the order is changeable. Then, so we can actually train a classifier. So that's the basic idea here. So in a sense, this is equivalent to noisy label classification problem. But as long as the test classifier is 50-50, then we don't have to care the noise, but just take the average of loss for two unlabeled data sets. Then this is an unbiased estimator of the risk up to a constant. So that's the result here. Then once we do more experiments for based on deep learning, so okay, I don't really go into the detail, but it works quite well based on some standard benchmark data sets. So UU method is close to PN learning. So PN learning is a fully supervised learning, and UU is completely unlabeled, unsupervised learning. But UU situation is applicable, for example, if we have two hospitals and collect data from two different hospitals, then we have two sets of unlabeled data. Then suppose we want to predict the existence of cancer or something, then we don't have to do any medical diagnosis, but we just collect unlabeled patient information from two hospitals. Then suppose that patient ratio in two hospitals are different theoretically, then that's enough. We don't have to do any medical diagnosis, but still we can train a classifier. So this is a kind of bit strange, weird method, but this is very strong because it's a completely unsupervised learning method. But we can have the same theoretical guarantee as supervised, fully supervised learning. And also experiments support our claim. So that's UU classification. Okay, any questions? It's a bit strange method, but it's a kind of noisy classification problem. Then we can somehow naturally understand the meaning of that. There's no magic behind. It's just a noisy classification problem. Okay, so then the next SU classification is a kind of variation of UU classification. So as I said, so now we have similar pairs. So two samples belong to the same class and like this. And also we have unlabeled data. Then, so we have basically two sets of data, two sets of unlabeled data. Then just decomposing these paired samples into standard unlabeled data. Then this corresponds to the classifier this. Then standard unlabeled data is having a classifier like this. Then we have two unlabeled data sets with different classifiers. Then we can just use the same UU classification algorithm to solve this problem. And also we can extend this to DU classification, dissimilar classification. My opinion is different as that person. These two guys have different opinions like this. Only from DU data, we can again train a classifier, basically in the same way. Then so SD is also possible. Then in the same way as PNU classification, we can also consider SDU classification. We have similar data pairs, dissimilar data pairs, and unlabeled data. We can train a classifier in a much better way. So that's SDU classification, and that was just submitted recently. Okay, then finally, complementary classification. So this is a bit different story. It's a multi-class problem. So as I said, labeling in multi-class problem is really time-consuming. So let's label this robot image. Then we have a long list of labels and find the right one. Boston Dynamics Atlas, for example, here. but selecting the correct class is really time consuming. So then let's use complementary labels. Now our data set is a pair of X and Y bar. So Y bar is a label that X does not belong to. And we assume that X, Y bar pair are coming from P bar IID. And P bar is the average of Px. So we assume that wrong classes are uniformly distributed. But if you have some prior knowledge, we can encode it here. But for simplicity, I just assumed it's uniform like this. Then only from X, Y bar pair, we try to train a classifier. So that's the setup. And again, so we follow the same standard recipe to define the risk. But now it's a multi-class classification problem. So notation is much more complicated. And maybe I don't really want to go into the detail. But for multi-class case, so we need to define first like C-class classifier. And it consists of 1 versus rest classifiers. Then loss is also defined in a multi-class way. So it's a bit complicated. But in the end, we have similar definition of the classification risk. So I don't really go into the detail here. But we want to estimate this only from P bar, not P. So it was just presented a couple of weeks ago. So the risk can be equivalently expressed in this way. So now we have L bar defined like this and P bar like this. Then, once we accept this expression, then we can just use like X, Y bar paired data, IID data, to unbiasedly estimate this term like this. So again, it's a standard empirical risk minimization. So derivation is a bit complicated. And we had also one previous paper that had more technically complicated paper. But we found that things become quite simple in the last ICML paper. So it's actually quite straightforward derivation. And we can really have a simple empirical risk estimator like this. So then, again, we can achieve van der Waals-Carothon convergence. Then, doing experiments. So, pconf method works quite well. And this is, we have two competitive methods, but this method seems to be working quite well. But actually, the main message is not really here. But let's come back to the crowdsourcing scenario again. So we asked crowd user to label this image. So that was an original way of collecting labels. But now let's convert multi-class labeling question into yes/no question. Instead of asking you to label this image and give you a list of labels, but rather pick one of the labels randomly and ask you, is this SoftBank paper? If it's yes, it's an ordinary label. And is this iRobot Roomba? No, it's complementary label. And in the standard framework, people just try to collect ordinary labels and throw away just complementary labels because they thought complementary labels are useless. But based on our theory, we can show that complementary labels also contain precious information, and we can train a classifier. Then again, we can just add risks. This is the risk for ordinary labels. It's a standard one. And then this is the risk for complementary labels that I explained in the previous page. And prepare alpha between 0 and 1 and just combine them. We can just tune it based on cross-validation. So then we can utilize both ordinary labels and complementary labels. So then actually this is really nice. Once we only use ordinary labels, it doesn't work so well. And once we use only complementary labels, it's much weaker. But if we combine them, then the performance is uniformly improved. This should be true, because we are adding more information, so we should gain more. And experiments really showed that. That was complementary classification. So then the final message here is, I didn't talk about models so far explicitly, but what I explained today is basically learning methods. So given data and given model, we gave a new training criterion based on data, based on some weak data. So supervised, unsupervised, semi-supervised. Reinforcement learning could also be allocated here. And then some weakly supervised methods here. Then this axis is basically orthogonal to model choice. We can combine whatever learning method with whatever model. Like, this is quite nice in terms of research and in terms of practice both. So in terms of research, so if you see like deep models, like the papers are uploaded to arXiv every day. So whenever you want to write a paper, you need to always check the latest arXiv paper and try to avoid some conflict. But we are orthogonal to that direction. So people are going this way, we are going this way. But whenever we had some method, we can always use the latest method. Like when we do theoretical analysis, we almost always consider linear models because it's the simplest and easiest to prove something. But when we do application research with some partners, we always use the latest model in like computer vision, CNN or NLP and LSTM and some other stuff. So our method is kind of model agnostic. So we can combine our method with whatever models. And also whatever regularizers, because it's a standard empirical risk minimization framework. It's nothing special. So we can put any other like spices on the basic framework. So here, so we try to explore this corner. So low labeling cost and high classification accuracy. And my talk had a lot of different sections, but the final message is that everything can be combined. So I talked about P, N, U, P-conf, N-conf, S or D or whatever. So everything can be combined because we are just estimating the classification risk in the same way. Then whatever piece of data you have, if you just give it to me, I can improve the performance. So that's the main message. So in the weakly supervised learning framework, so we want to collect whatever piece of data, piece of information we can get and try to improve the performance. And this approach actually made it possible. So we may consider maybe more different type of weak supervision, but as long as we can estimate the classification risk in the same way, then we can also combine them. So we decided to write a book and publish from MIT Press, and hopefully 2020. I just started writing, and it takes maybe 1 or 2 more years, but hopefully we can publish the kind of general framework of weakly supervised learning. Okay, so this is the last slide. Thank you very much. Any questions? Yes?
Any insights in regression direction?
Yeah.
There's lots of spaces there like unlabeled, right? No label.
Yeah, that's a very good point. But regression and classification are quite different. Like positive, negative, unlabeled. So unlabeled is the same, but we can't use the same trick here. Like we can extend this PU, PNU approach to like ordinary regression, for example. So it's like class 1, 2, 3, 4, 5. It's ranked. We can extend this approach to that problem. But pure regression is actually quite different from standard classification. So far, I have no idea how to directly extend this idea to this regression problem. But if you have some ideas, that would be great to have more discussion. Thank you.
Any other questions?
Hi. Thank you for the presentation. I'm also curious about your opinions about multi-labeled data, because nowadays lots of data are crowdsourced, and that also brings the problem that they are also noisy. So I'm curious about your opinions.
Yeah, so thank you very much. So I believe multi-label is also part of like weak supervision. And we have actually some extensions behind, but they are not published yet. But we can somehow naturally extend this kind of approach to multi-label scenario.
Thanks.
No other questions. Let's thank our speaker again.
Thank you very much.